Well, good morning, everybody, and welcome back to our Friday edition of AP Calculus BC Live. If this is your first time joining us, I want to welcome you and introduce myself. My name is Brian Passwater. I'm an AP Calculus teacher at Speedway High School in Speedway, Indiana. You can see on the screen on the bottom corner there is our logo. You might not be able to tell what it is, but it's a spark plug. We are the Speedway spark plugs because we are right next to the Indianapolis Motor Speedway in Indianapolis, Indiana, which is the home of the Indy 500, which is commonly known as the greatest spectacle in racing. I want to give a big shout out to my AP Calculus students who are enjoying the first day of their well-deserved spring break, which started today. And I'm sure, like many of you, they've been working incredibly hard these past few weeks as we've been learning together how to navigate and do all this e-learning and distance learning. For my class, I don't know about you, but we've been doing some live Zoom sessions daily, kind of like we're doing here, except for my students are able to more interact with me because we don't have uh, 2, 3, 4,000 students on at a time. And I don't know if you guys are doing anything like that at your own school with your own teachers. I know that some schools aren't even allowed to have any instruction right now, and some schools are. But it's always interesting to me because for my own students, every day we get on Zoom, and the very first thing we ask, right? You would think something about calculus, about the homework. No, the first thing we ask every single time, or that they ask me, is what did I have for breakfast? We have morning sessions. They always want to know what I have for breakfast. And so this morning, in case they're watching, I know they want to know. I had a nice little V8 for breakfast this morning, a couple of oranges. So I am geared up and ready to go. So I hope that you too, because we're going to have a really great session today as we wrap up our discussion on parametrics. And so before we get into all of that, I want to share you something. Look at this. This is a screenshot from Wednesday, right? So we started these live sessions on Wednesday of this week. And as we were planning these, as College Board was planning these, this is not something that had been in the works for a year or 2 years. This is something the College Board decided they wanted to do with all the schools being canceled and a lot of the anxiety that was going on around with teachers and students about, we've been working so hard for 7 months. What's going to happen to the AP exams? I can't be in school. How am I going to be ready for this test? And the College Board really said, look, we got to do something. And so they found some presenters and some teachers to say, would you be willing to step in and do some live virtual lessons that can be recorded for our students to get them ready, not just to learn the rest of the material during the curriculum, but also to get them ready for the AP exams in the month of March and May, or March and April leading up to May. And so we kind of just jumped into this. And so I remember on Tuesday, the night before we were getting ready to have our very first session, I was talking to my wife, kind of getting ready in the evening, and she knew that I've been working on these sessions with my co-teacher, Tony Record. Many of you saw him present yesterday, and she knew that we were working on these things, and she kind of started asking questions about it. And it occurred to me, I didn't do a very good job of explaining to her what was going on because she knew that I had been doing Zoom sessions with my own students. And she knew that this was going to be cast on YouTube Live, but we're using Zoom as sort of an intermediate app to get us there. And my wife thought I was talking to my students today. And so I guess you guys are all sort of my honorary students today, whether you're a student or a teacher. But when we were talking about it, I couldn't figure out whether we were going to have 10 students join live, 50 students, no students, 100 students, but never in my wildest dreams did I ever imagine that on Wednesday, live at 9 a.m. Eastern, 6 a.m. on the West Coast, we had up to 4,500 of you joining live for the first Calculus BC session. And on top of that, in the day and a half since we ended that session for our first one, we have over 45,000, 45,500 of you have viewed the video. Maybe it's just a couple of you just liked it so much you watched it like 100 times in a row. I don't know, but 45,000 of you have watched this, and it's not just AP Calculus. I went on the YouTube channel for College Board today and just grabbed a couple of screenshots, and these are some of the videos for the other AP classes that have happened. And you can see these are brand happened, 2 days ago or yesterday. 77,000, 25,000, 18,000, 75,000, 40,000 views. And so it occurred to me that just as I'm proud of my own students for all of the hard work that they've been doing, I'm extremely proud of all of you as well. My students have embraced this challenge, and they've committed to not letting the circumstances or the obstacles that have kind of been thrust in front of them this spring semester become a barrier or become an excuse. They're working even harder to overcome those things. And if you're joining us live or if you're watching the recording, you're doing the same thing. So we're very proud of you, and we're excited that you're joining us. And we feel like if you join these each day, that you really are going to get better each day. And when the exam does finally come here, you guys are going to be ready for it. You're going to be successful, and you guys are going to do a great job. So every day that we're on here, we have some materials that you'll see me writing on them, and you have access to those materials. So if you want to get the materials and print them off before the session so you can follow along with them, or even after the session, if you want to print them off, you can go on the YouTube channel, and underneath the title, you're going to see kind of on the bottom there a link, and you can kind of go right past the thumbs up, right? So if you go down past that little thumbs up, maybe click on that on your way down if you would like to, maybe by accident, that's okay. But you're going to see this little live link right there. And it's the same link every single day. And then you're going to be able to click on that, and it will immediately take you to a Dropbox folder. And in that Dropbox folder, you're going to see all of our handouts. So each day we'll keep adding them. And then also after we add them, uh, after the lesson, we're also going to post probably later that evening or the next day the written, actually typed up solutions for all of those problems. So in these lessons, we're not going to be able to do every single problem on the handouts. We're purposely including additional questions that we're not going to be able to get to. That way, as a teacher or as a student, you can either assign them to your students, or as a student, you can just do some extra problems to get some more practice. But we will have the typed up solutions there for you to check along the way. And I didn't even think about this, but Tony Record, the other teacher, and I, we each have our own Dropbox that we share, with teachers and things like that. But we wanted to make sure that we created a different Dropbox that wasn't linking directly to us for these sessions. And so I was making this Dropbox folder last week, and you have to put a name and all that kind of stuff, email address. And so I just wrote down Isaac Newton for the name, not even thinking it would matter. But if you'll look, when you get that little link, you're going to see the Dropbox folder that says Isaac Newton shared this with you. So I think that's kind of apropos and serendipitous, because Isaac Newton is sharing the calculus with you, but now also he's apparently sharing some nice resources and materials that you could use during the lesson and after the lesson as well. So what's going to happen today, what's going to happen next week, and what's going to happen down the road? So today is Friday, March 27th, and we are looking at topic 9.6 in the curriculum. This is our last topic that covers parametric functions and vector valued functions. Um, and then next week, we're going to kick off our beginning of series and Taylor polynomials. So next week, it's March 30th, Monday through Friday. So this week we started on Wednesday, but from here on out, we will meet every single day of the week, Monday through Friday, all the way through May 1st. And so next week, these are our 5 topics. You might see some little asterisks next to some of the topics, and some of them don't have asterisks. What that means is, I'm sure you probably know by now that the College Board has worked with some universities to figure out a way to reduce some of the content of most of their AP exams for this year, and this year only, due to the extenuating circumstances. And asterisks are the topics that are still going to be tested on this year's exam. So you might be wondering, so today's lesson does not have an asterisk, and a couple of the lessons next week don't have asterisks. What's the point? Why are we doing these lessons on things that aren't even going to be on the exam this year? And so it's a really good question. I'm glad I asked it. But I want to make sure that you hear this clearly, because there's a lot of good reasons of why we're still covering things that are not going to be on this year's exam. First and foremost, even though it's not in the exam this year, it is in the curriculum, and universities do expect that students will have seen these things and know how to do them as you move on to future courses. And so we're not just trying to get you ready for the exam that's going to happen here in 6 weeks. We want to make sure that you're successful way beyond the exam. So that way, when you go to college next year, if you take the next course in the math sequence, that you will be in a good position to be successful beyond what we're doing right now. Now, something that's probably a little bit more immediately gratifying to you as a student or even a teacher, these topics that we're doing that are not tested are still really rich. And so we're not covering every single topic that's not tested. We wouldn't have time for that. But Tony and I worked really closely with our friends at the College Board and some other math teachers to make sure that we chose some really purposeful topics. So even though they're not tested, we can do a lot of review and AP exam prep, AP exam practice with strategies with them. And if you joined us on Wednesday or Thursday when Tony presented yesterday, you probably noticed that we're doing a lot of things that are tested. So we're doing it in this kind of this new context of parametrics, but we're reviewing a lot of the things that you're going to see on the exam this year and a lot of strategies. So we're weaving all those things in there. So that way, every one of these sessions will not just help you for down the road when you leave high school, but they're also going to help you in May or June whenever you ended up taking the AP exams, whenever those are released. So speaking of that, be on the lookout April 3rd when the College Board is going to release some more information about the exams. I know that we're all anxious and excited to see what they come up with. I know they've been working really hard to make sure they give us a really good test that's going to be measurable of what you actually learned this year. So that way you can earn those credits that you've been working so hard for. So we are going to do a lot of things that are going to be helpful on the exam, even if they're not directly tested. And then you'll notice on April 13th, 4/13, I'm kind of fast forwarding a little bit here. We're going to spend 15 consecutive weekdays, right? So three weeks, just doing nothing but AP exam prep and review. And I'm going to tell you right now, if you come to these sessions for the next 2 weeks, and you come to those 15 sessions, the 3 weeks after that for the exam prep, it says on there BC exam prep, but we also know there's going to be some AB problems on the BC exam. So we're going to be reviewing all of those things, kind of tying AB and BC topics together. You are going to be incredibly prepared. And I feel like if you can find a way to watch all these videos or join live for these videos each day, you're going to come into that exam and you're going to feel like you are incredibly well prepared for it between the efforts of your own AP teachers that have been working with you every single day this year, doing an incredible job, as well as some of the things that Tony and I can share with you virtually to prepare for the exam. So put that on your calendars because it's going to be an incredible opportunity the College Board is allowing us. So we are going to jump into the warm-up, and I'm going to get a drink here. I apologize. We started these sessions on Wednesday, and I forgot to bring a drink with me when I started, and my mouth got more and more dry as we went. So every day we do these warm-ups, and the warm-ups are going to be the follow-up from the previous lesson. So at the end of each lesson, we're going to leave you with an AP exam practice problem, kind of as homework. And we really do encourage you to do that. They should take you about 5 to 10 minutes to do, but these problems are going to be really the heart and soul of how do you get ready for the exam? How do you prepare for the kind of questions that the College Board is going to present you with whenever you sit down for the test? And so the best part about these is that every one of these problems that we do are going to be new and unique. They haven't been on an AP exam before. They haven't been in a textbook. Nobody has been using them yet. They're questions that I'm writing and Tony and I are writing that are different, that are connecting ideas together, and they're things that will get you ready for the conceptual depth of understanding that the exam is going to want to see out of you. So we're not going to have you do this on your own right now because during the warm-ups, we're going to just kind of walk through them together after hopefully you've tried them. But they're really good opportunities to start preparing for the test. So in this problem, I'm going to kind of walk us through it, and then I'll go through the answer with you. There's a lot going on. And if you were at Tony's session, you noticed that we have two different particles. We have particle P and we have particle Q. So there's two different things happening, and they're kind of moving through the plane. P and Q both are. And then we are given some positions. We know that particle P's position and particle Q's position at time 0. And we also know a little bit about the particles themselves. Like, for example, we know that x prime of P is given by the graph. And we also know that the graph is simultaneously y of Q. So the graph is the derivative of x for particle P, and the graph is also the y value for particle Q. And then we're given the y value for particle P separately as this quotient. And then we also know that x prime of Q, x is derivative for particle Q is given by this piecewise function. So a lot of things are happening here. We have lots of different letters, lots of different directions. We've got a graph, we've got some data, we have an equation, a piecewise function. It can be a little bit overwhelming when we first see these problems. So really show you the importance of being well organized, being careful to pay attention to details, reading questions carefully, and then learning to break down what's really important, right? I think sometimes what happens is we get overloaded, overwhelmed at the questions. I know for years, my calc students have said, as we do AP problems, they'll do one and they'll just be completely stumped. I mean, they won't even know where to begin. And then as we start going over it, I'll kind of share a couple of things about it. And as soon as I'll kind of rephrase or talk about what it wants in a kind of a different wording, it will click immediately. And the kids will be like, well, why don't they just ask that, right? And the fact is they did ask that, but they just ask things sometimes in clever and unique ways to see if you really understand what's happening or whether you just kind of memorized a few formulas. And so if you want to be really successful in AP calculus, we have to really get to the understanding of what's going on more than just trying to memorize some patterns and some examples. So let's go through this warm up quickly, and I think you're going to see um, some nice strategies that will help you tackle problems like this. And this is probably the very high end of the complexity that you could possibly see, right? Because there's so many things happening here. But you could definitely see, a problem that might have a graph for part of it and an equation, or two different particles could be going on. But I kind of threw everything together just so you can see all the possibilities that you might be faced with. And so in this case, I'm just going to jump into part A and notice what I'm going to do is I'm going to look at the question and we're going to underline, analyze, and kind of interpret what it wants. And so I think one of the traps that students fall into on AP exams is we get so caught up in the information that we try to use that as we're solving the problems rather than just look at the problem by themselves. If we sort of ignore all of this stuff up here and look just at the question, we're going to have a much clearer path of what to do. And so don't try to use the information yet. Let's think about what the question wants and not worry about anything else. And so part A says, find the speed of particle P. Well, Tony talked about that yesterday in the lesson, right? That in parametric motion, we know that the speed of particle P at time 4, well, we have a nice formula for speed. And at time 4, the speed formula is going to be x prime of 4 quantity squared. I'm just using our equation or our expression for speed, plus y prime of 4 quantity squared. And the entire expression is square rooted, right? That's our expression for speed. And so now that I've written that down, I've ignored everything else, just written that down, and now I've got sort of a blueprint. All right, that's where I used blue pen. That wasn't completely coincidental, I promise you. But we have this blueprint of how to solve this problem. If I'm going to solve this, I've got to figure out what x prime of 4 is, and I've got to figure out what y prime of 4 is. So now I know what to look for. And as a matter of fact, I'm going to add one little piece here because since we have two different particles, it's important to realize that both of these values are for specifically particle P. And so now I want to go figure out, okay, how am I going to figure out what x prime of P is? Well, if I kind of look around here, remember the graph they gave me up there, this is a graph of x prime of P. So if I want to find out x prime of 4 for particle P, I just need to go on this graph at when T is 4, which I can see is right there. And I can see pretty quickly that x prime of 4 in this case is 2. I'm going to square that value. And then now I have to go and figure out how I'm going to find y prime for particle P. So I'm going to look around for y prime. And I don't really see a y prime anywhere, but I do see right here at least an equation for y, right? So if I want to figure out y prime for p, then I can differentiate this, right? And so y sub p, so y prime of that, I'm going to take this derivative. And I mentioned earlier that all these problems are going to have some good review of things that are tested. Well, here's a good example because we have to differentiate this. And because it's a quotient, we're going to have to do the quotient rule. And so we're going to do low d high. So we're going to get x prime for particle p of t times, so that's low, right? And then d high, so top derivative is 3, minus high, so that's going to be 3t, times the bottom's derivative, and that's going to turn into x double prime of t all over the bottom squared, right? So we have a nice little example where we can use the quotient rule. So even though we're learning a new idea, there's some really good previous topics that are in there that are going to help us review for the exam. And I want to find this value again at 4, right? So it's going to be y prime of p at 4. So I want to plug 4 into all of this. And so we're going to get x prime of 4 and then times 3. And then we're going to have 3 times 4 is going to be 12, right? Then we're going to have x double prime of 4 all over x prime at 4 squared. Man, this problem's awesome, isn't it? I wish I could figure out who it is. So x prime of 4, well, we already figured that out, didn't we? That was already something we figured out. So x prime of 4 was 2. So we're going to get 2 times 3. And then we're going to have 12. And now I got to figure out x double prime. So this is another good connection, is that if you're given x prime and you want to know x double prime, this is really just the slope, isn't it, of x prime. And so we're given a graph of x prime. So at 4, the same location, I want to figure out the slope right there. Well, the slope of this line is just -1. So that means x double prime of 4 is -1 all over x prime of 4, which we said was 2 squared. And that ends up giving us, if we simplify this a little bit, 6, and then we're going to get plus 12 over 4, and that's going to be 9 over 2. There we go. And then finally, if we look at part B here, it says set up but do not evaluate. We see those a lot on the AP exam, that we just want to set problems up to see if you understand them, but we're not going to be as interested always in having you complete all these. So let's figure out an expression that would give the total distance, right? So that's a key word there, total distance traveled by particle q. And Tony also taught this yesterday. This is a really good warm-up to kind of review what Tony did. The total distance formula is going to be from the integral from 0 to 5, right? And then we're integrating speed, right? That's our formula for total distance. And so it's going to be the square root. And again, we're doing particle q this time. So it's going to be x prime of t for particle q. It's a lot of letters going on there. And then plus, and then same idea, we're going to do y prime of t for particle q, quantity squared. And then now we're not going to plug numbers into here because we're integrating this, right? In the previous example, we plugged 4 directly in because speed is a magnitude, right? It's a scalar, and so we can plug something into it. When we're finding total distance, this is now an expression in terms of t. It should have a dt at the end there, so we can integrate it. And what we're going to end up doing is we're going to try to find some expressions that we can plug in. We can't leave it like this for the AP exam because we don't have this in terms of just t like we need to. But we do have an equation for x prime of t, don't we, for particle q? X prime of t for particle q is this. And notice what we have. It's a piecewise function. And the piecewise function is 2 pieces. The first piece is from 0 to 3. And the second piece is from 3 to 5. And so what we're going to have to do is we're going to have to break our integral up into 2 separate integrals. Another really good review, something that we've learned in the earlier part of the year during the AB portion, you can integrate something, if it's a piecewise function, we're going to break it up into 2 parts. So we're going to integrate this from 0 to 3, and then we're going to add a separate definite integral from 3 to 5. And that'll allow us to use those properties of integrals to add up those 2 finite integrals. So x prime of t, or x prime of t for particle q, notice we see that it's just going to be 2 times t there, right? Quantity squared. Then I have to figure out y prime of t for particle q. And so if I kind of look up here, I'm trying to find particle q, and notice what we have in the graph here is y sub q, right? And so from 0 to 3, we see that y of t is this graph right here that I'm kind of highlighting in blue. I'm going to kind of erase the earlier part that we're looking at. This is y. So from 0 to 3, think about y prime would be, right? Y prime from 0 to 3 is just going to end up being 0, isn't it? Because the slope of that segment it's horizontal, so we know it's going to be a slope of 0. So this is going to end up being 0 squared. And now I'm going to break it up to the other part as well. So now we're going to go from 3 to 5. And we have to do the same idea. We're going to do x prime squared. So now we're going to have sine of t squared. And then same idea for the y prime. But now from 0 to 3, we have the segment right here. And I should have made that in red probably. So if I make this one in red, this is the second part, right, from 0 to 3. So in that part, y prime for particle q, again, is the slope. Well, it's still linear, and the slope is constant. The slope is going to be a constant of -1. So I can go back up here and then do -1 squared dt. And notice the instructions said set it up, which we did, but do not evaluate, meaning don't work it out, don't complete it. So we can leave our answer like this, can't we? We couldn't have left it as it was in the beginning because first of all, we can't compute this without breaking it up. And second of all, we can't have functions in our setup. We have to turn things into expressions with only t in them, not x of t or f of x or something like that. So there's the warm up. It was a pretty hardy problem, I think. A lot of good examples in there to sort of build on what you guys did with Tony yesterday. So let's take a look at what we're going to do here for the next 20 minutes or so together. We're going to be kind of putting all these ideas together, right? So what are we going to do? Well, we can talk about finding the position of a particle using parametric functions. And if you've done particle motion earlier in the year on a straight line motion on the x-axis or y-axis, same exact idea, but now we're going to extend that to parametrics. So we're also going to be connecting the concepts of motion that we've learned. So we've got a little bit of motion here for Unit 4 and Unit 8 and Unit 9. So we're going to connect all those ideas together to kind of look at this more cohesively. So what should you know to be best prepared for this lesson? Well, hopefully you're comfortable with solving motion problems that are straight line motion. That would be in terms of along the x-axis and along the y-axis. You should be comfortable differentiating parametric equations. We did that on Wednesday during our first session. And then also that you're able to connect the concept of position, velocity, and acceleration, that we know we can differentiate or integrate to move up or down sort of that ladder. So by the end of this, what will you be able to do? So we're not going to actually solve this problem. And to be honest with you, I'm not even sure how nice it would be to solve this. I wrote this problem knowing it'd be here without actually working it out or thinking we're going to do it. So I'd be curious to see if anybody tries to solve this problem and see what it ends up being, if it becomes nice or even doable. But the kind of questions that we're going to see are going to be particles moving in the XY plane. The position is given by the parametric functions x of t and y of t. And we know that x of t, the x position, is sine of t squared. And then we don't know what y of t is, but we do know that dy dt, the derivative of y, is directly proportional to y. By the way, I wrote this wording as sort of like a homage or shout out to our friends that are doing the Calc AB videos, Verge Cornelius and Mark Corrali. If you've been on their sessions yesterday or even on Wednesday, they were talking about interpreting these differential equations like this. They're doing a lot of problems like this. So if you were in their Wednesday session especially, you should be really comfortable writing that. And so at time 0, we were given a position, and we want to know what the position would be at time 4. So really the question today, the only new idea that we have to sort of extend our learning with is going to be, how could we find the position of a particle in parametric form by extending our understanding of particle motion? I keep saying the word extending because if you've done the particle motion earlier in the year, a particle or a bug is moving along the x-axis. This is the motion that we would see in a typical Calc AB course. If you've done that motion, then you have all the tools that you need to do parametrics. You're going to be able to do all these problems just by doing these as treating as x and y as two kind of separate problems. So you're going to find these problems probably very doable. So let's look at a couple of examples. And before we jump into those, I want to point this out. Again, this is in the Dropbox link, right? All these materials are in the Dropbox link, but I made a little kind of one sheet or a quick sheet, I call them, for my kids, where I kind of take all these big ideas, because we might spend in class 2 weeks, right, doing parametrics, all kinds of stuff. And so you have all these different notes and handouts, and you have formulas on different ones, but it's really nice at the end of it all to have a nice one page with all those ideas, those big concepts and the formulas together on one in one place, right? And so these are kind of the big ideas that we're talking about position. We're using vectors, right? Tony talked about the word vector yesterday. Essentially, we're looking at it as an x coordinate and a y coordinate, but each of those is defined by time rather than each other. And so x of t is our x coordinate and y of t is our y coordinate. And then we can find the position. And this is just the x position, right? So if we're trying to find the position of something, we can use our sort of accumulation model. In our accumulation model, we have x of a plus the integral from a to t of x prime of t dt, right? So we know to find any value of any function, it's going to be a starting value plus the integral of the rate of x prime. And we could do the same exact equation with y to figure out the y coordinate. It would just be kind of parallel. That y of t, the y position, is going to be a starting y value plus the integral from a to t of y prime of t dt. So we can, this is what I mean when I say we can extend our understanding, because we've done these kind of problems in earlier in the year with Calc AB, and now we can just do them separately to figure out how to do the same exact problem in parametric motion. We know that the velocity vector is just going to be the derivative, the velocity in the x direction and the velocity in the y direction. We can write that as y prime or x prime, or we can write it as dx dt and dy dt. You need to be ready to see both of those. They're the same ideas. And then the acceleration vector, as you might imagine, is just the derivative of that. And so x prime becomes x double prime, and y prime becomes y double prime. And as Tony talked about yesterday, we have this idea of speed in parametrics. And speed in parametrics is just the square root of dx dt squared plus dy dt squared, which leads us directly into our total distance traveled. And that's just the integral of speed, which is the integral from a to b of the square root of that speed expression that we found. And then on Monday, or on Wednesday, I keep thinking that we started these on Monday this week, but on Wednesday during our first session, I kind of led us through the idea of dy dx, which is the slope of the tangent line to a curve. And the slope of a tangent line is always dy dx, but if we're given parametrics, we can find that by doing dy over dt divided by dx over dt. And this little last piece here, I kind of snuck it in on the bottom, hoping maybe you wouldn't notice. This is how we find the second derivative with respect to x. This was that topic 9.2 that we kind of skipped over because we only had a few days and a few topics that we could cover. But Tony and I are going to be making a little supplementary video that we'll put in that same Dropbox link. When you go to that link, you'll see a folder that says supplementary videos. And we're going to end up putting one of those in there, maybe 10, 15 minutes, kind of walking you through this idea and giving you a couple of examples for it. That way you'll be be exposed to them and kind of see how to do them. So with all that information at our fingertips, let's try a few of these practice problems. And again, we're going to incorporate a lot of things that are things that you know from earlier in BC or AB mixed in with these ideas of parametric equations, as well as combining a lot of the skills the mathematical practices that the exam is going to test you on. And so one of those is going to be seeing things in different forms, whether it's graphical or algebraic, whether it's dx dt or y prime. All these things are going to be things that are going to be helping you to prepare for the exam. And so our first example we're going to do together is the position of a particle is defined in parametric equations as x of t and y of t. So we have our x value and our y value. And dx dt, so that's kind of x prime, right? We talked about how that's another way of saying x prime of t, is given by this. And dy dt, y's derivative, is given by the picture. So we don't have an equation for it, but we have a nice little graph of it. That's why it's labeled as y prime up there, right? Because that's the same thing as dy dt. And it consists of a line segment and a semicircle. And we know that at time 3, at t equals 3, the particle is at this position. So that means that x of 3, that's our time, must be 7. And y of 3 is going to be equal to -1. So we're going to find the position at time 0. So if you remember from the previous slide, I talked about how to find the position, right? On the previous slide, we learned that the position of a function is just going to be the initial position, and then adding to that the integral from the starting time to the ending time of the derivative of that function. And luckily for me, my pen decided to freeze up here for a second. So let me see if I can unfreeze myself here. Wonderful. I don't think it wants to unfreeze for me all of a sudden. There we go. Sometimes when you get on these smart notebook files, you do a lot of things at once, it kind of frees up on you. So here we go. So we have, if I want to find the position at time 0, we're going to have, let's find the x value first, right? So I think with parametrics, the big key is realizing we're just going to find the x position and we're going to find the y position separately. Okay, so to find the x position at time 0, we're trying to find x of 0, and x of 0 is going to be the starting position. Well, what do we know? We know that x of 3 is 7, so it's going to be x of 3, that's my starting position, plus the integral from 3 to 0, my starting position to what I want to know. And I realize those are kind of reversed right now, so we can deal with that here in the next step by using some properties of integration of x prime of t dt, right? So to find any final value of any function, we have a starting value plus the integral of the derivative or the rate from the starting time to the ending time. And so in this case, I've got to find a way to integrate this. X of 3, by the way, we know is 7. And I'm going to go ahead and subtract, right? We can flip those limits of integration using our properties of integrals. I want to reverse those so that with the lower numbers on bottom, I just make the integral the opposite. And then x prime we're given, and x prime is equal to 8t e to the 2t power. And now we got to find a way to integrate this. And so if you're a BC student, hopefully you are right now, what do you think we're going to do, right? Take a couple seconds and see if you can recognize what the best strategy is going to be to solving this problem. I'm going to give you about 15 or 20 seconds to think about this for a few seconds. So whenever I see an integral, my first instinct is thinking u substitution, because that's pretty much the dominant way that we integrate things. But in this case, it's not going to quite work out because of this extra t that we have in the problem. And hopefully you recognize it's kind of like a product, isn't it? And when we have a product of two things where we can't use u substitution, typically for Calc BC at least, that's going to end up being a integration by parts problem, right? And so I'm going to do this tabular method. Hopefully you've seen that a little bit. I think tabular method is a nice way for us to kind of organize things and keep things clean, especially when your u is going to be a polynomial, something like x or x squared or something. So in this case, I'm going to make the u for integration by parts just be the 8t. And then I'm going to make the e to the 2t become my v prime. And then the way we use tabular method is whatever you choose for u, we just keep differentiating that until we get down to 0. So 8t becomes just 8, and then 8 becomes 0. Then if I'm integrating this, the integral of e to the 2t, we could do some u substitution, but it kind of helps to understand the properties and how integration works and how u sub works. U substitution for integration really is just the inverse or the reverse of chain rule, isn't it? And so instead of taking the derivative of e to the 2t, we're integrating it. So we know when we integrate this, it's still going to be e to the 2t. But instead of multiplying by 2 like we would if we were differentiating it, since we're integrating it, we're going to divide by 2 or multiply by a half. And then we have to do it again, right? We have to go all the way down till we kind of have our zero, we match our zero term here. And so I'm going to integrate this again. Well, the integral of e to the 2t, like we just said, was e to the 2t times 1/2. Well, we already have a 1/2 there, so now it becomes 1/4. And when we use the tabular method, we use alternating signs, and then we kind of connect these diagonal terms. And the product, the sum of those products, are going to end up being the indefinite integral, right? We could have easily done this by using the integration by parts, the formula as well. Sometimes doing things tabular method on problems like these make your life a little bit easier and quicker, although we still need to know the formula for certain problems as well. So in this case, we're going to get, if I integrate this, 8t times 1/2, that's going to give me 4 times t, e to the 2t power, and then minus 8 times 1/4, which is going to be minus 2 e to the 2t power. So this is what we get for this integral here, but we're integrating it from 0 to 3, so I really need to put my limits on there. And if I'm plugging these in, if I plug in 3 first, we're going to get 4 times 3 is 12, e to the 6th power, and then plug in 3 to the second one, we're going to get 2e to the 6th power. And then I'm going to subtract. You notice I put an x here, didn't I? You get so easily caught up in writing x all the time, it's easy to let those slip in there. And then we're going to plug in 0. If I plug in 0 to the first term, well, 4 times 0 is going to be 0. And then minus 2e to the 0 power. Sometimes I have to remind my students that when you plug 0 in, a lot of times it just becomes 0, but not all the time, right? So you can't just automatically assume if you're going to have 0 for one of your limits, the answer is going to be 0, because it doesn't always work out that way. So in this case, we have 12e to the 6 minus 12, or 2e to the 6. That's going to be 10e to the 6th power. And then on the other parenthesis, 0 minus 2e to the 0 power, well, 0 minus 2e to 0 is just going to be negative 2 inside of there. And now I'm going to combine these, and we're going to get, if I kind of move up here, this line, and we're not going to forget about this little thing here in front, are we? So in front of this, we have 7 minus quantity. All this work we were doing was just to figure out what this integral was. So I want to make sure I put that in brackets. 7 minus 10e to the 6th power plus 2, because I'm going to distribute that negative sign. And then I can distribute the actual subtraction sign, and we're going to get 7 minus 10e to the 6th, and then minus 2. And that's going to give me 5 minus 10e to the 6th. All of that was our way of finding what x of 0 was. That was a lot of work. Hopefully finding y of 0 won't be quite as bad. I'm going to do that in red pen, so that way we can kind of keep these two ideas separated, right? And so y of 0 is going to be the same general idea. Y of 0 is going to end up being y of 3, because that's the time that we are told, right? Plus the integral from 3 to 0 of y prime of t dt. And then this time we're actually given a graph of y prime. And so finding the integral from 3 to 0, I'm going to go ahead and again use that same property of limits. It's going to be -1 minus the integral from 0 to 3. And now I got to figure out what that integral is from 0 to 3 of y prime. Well, this is a graph of y prime, and I'm going to do this somewhat quickly so that way we can kind of jump ahead here in a second. But finding the definite integral is finding the signed area. And so this is kind of a weird shape. And so how am I going to find out the area? It's wanting the area, the signed area between the curve and the x-axis. And so really it's going to be this shape right here, this little triangle. And then whatever this little shape is here, it's like a wedge between the circle, and the same idea here. Well, how are we going to compute that? How would I come up with that? Well, the triangle part is going to be fairly easy, because for this part right here, since it's below the x-axis, it's going to be negative, and we're going to have -1/2 base times the height. So it's going to be -1/2, 1 times 2. And then the rest of the stuff is still below the x-axis, so it's going to be minus again. But here's how I'm going to approach this problem. Maybe you do it a little bit differently. If I want to figure out this red part, I'm going to think about this as one big rectangle, and then I want to cut out this sort of half a circle inside of it. So I'm going to think about this as, how would I figure out the area of the red part is going to be the rectangle? Well, the rectangle there is going to be 4 times 2, right? Base times height. And then I want to cut out this half a circle. So I'm going to cut out a 1/2 pi r squared. And r in this case is 2. We can see that pretty easily. And then that entire thing, right? 4 times 2 minus the half a circle, that will give me the red part. But since this was underneath the x-axis, that's why I am subtracting it. And so if I bring back what we had in front, right? We had a -1 minus all of that in front. So this is going to be a little bit ugly, I think. And thank goodness on the FRQs on the exam, we don't really have to simplify on the FRQs, but we're going to have -1 minus all of this whole thing. -1/2 times 1 times 2 gives me -1. And then this is, if I distribute this other minus sign here, it's going to end up becoming +8 inside of there. And then, sorry, that's still -8, isn't it? I'm getting a little bit ahead of myself. This is a -8, but then negative times a negative becomes plus, and now we're going to get 1/2 pi times 2 squared. And we could simplify that. I want to not simplify it now because of time, but if you look on the answer keys that we have that we'll be posting to that Dropbox file after this, you'll be able to see the simplified answer. And then we can finally answer the question because we want the position. The position is going to be the coordinate that we found here, right? This is our x of 0 position. And then we can write that as an ordered pair. We can write that as 5 minus 10e to the 6 is my x coordinate. And then our y coordinate was this expression right here. And because I'm running out of time, we'll do that. Please, on the AP exam, don't draw an arrow to a blank space. Go ahead and make sure you show all your work. Okay, so I'm going to highlight a couple more problems that you could try on your own. The next example is, now we're starting to take things that Tony did and that I did on Wednesday, and we're blending them together. And so this is a really good table problem. It involves acceleration, and it involves velocity when the particle's at rest. So try this problem out. The algebra is pretty straightforward on this one. It's not a really heavy algebra problem like the last one was, but it really makes you, connect some ideas together. And so that's a really good problem to try. We also have a problem involving speed, but instead of giving you time and you find the speed, we're going to make you do this in reverse. We're going to tell you the speed, and then you're going to go backwards using that same speed formula to see if you can figure out what the time was. Another really good problem that doesn't require heavy algebra, but there are some really neat connections in there. And then in the file, if you have printed it off, if you see it, there's kind of a card sort there. And what you're going to see is, this is just one example where I'll give you, there'll be like 5 Roman numerals, right? So we have this practice stem here. So at any given time, a particle is moving along a curve with that position, and we're given some information about x prime and y prime. So we're given both of those derivatives, and we're also told where the particle's at time 2. And so we're not even solving these problems, we're just getting this set up, right? So the most important part of any AP problem is just understanding what it's asking and what approach you should take. And once you can do that part, then all of that skill, all that practice you've been doing all year is going to kick in. You can start doing the derivatives and integrals and things like that. But this is, which one of these would tell us the total distance traveled. And so there's a lot of small mistakes. And so there's a lot of answers here that are close, but not quite right. And Tony did a similar example in yesterday's notes for that as well. And then on the next slide, this is the rest of this card sort. So there's actually 5 Roman numerals. They're asking you to find 5 kind of similar ideas. This is kind of encapsulating all the things that we've done. And there's several different little choices here, I think it's A through Q or something like that. And so you're going to look through these choices and figure out which one matches up with each one of those choices. And so you'll be able to hopefully kind of drag them over. So x of 5, we kind of mentioned a minute ago, how would we compute something like that? Well, we would take a starting value, which is going to end up being x of 2, which is 1. And then we're going to add the integral to that of x prime. And so on a problem like this would go together. But a common mistake that students make is something like this choice D, because they mix up the 1 here, the X value, with the time value here. So it's kind of a nice little card sort. It doesn't require you to solve things out. It just makes you kind of make those connections so you can really get a lot of good practice by trying to figure out which ones go with what. And then I had to give a quick little shout out to this little field goal problem. Jevi and Ben are practicing field goals, and you're going to figure out based on the information whether he's going to clear the uprights or not. One little thing I'll point out to you to be careful for is the equations are in yards, but the uprights are 10 feet above ground. So whatever answer you get, you have to be careful to make sure that you're not answering yes or no without thinking about if you're in the same units or not. And those problems again are going to be worked out in those solutions for you as well. So a couple more nice little practice problems here that you'll be able to do, and I think you'll end up seeing a lot of good examples that you haven't seen before. There are some things that are similar if you've done some AP problems or book problems, but I always try to throw in some twists that you haven't seen or see things in new ways, because the AP exams are going to do that, right? We know the exams are going to show you things in ways that you haven't seen before. And so the only way to get ready for that, how do you get ready for something that you haven't seen before? Well, it's to practice things that you haven't seen before. The more you practice and adapt and understand and make those connections, the better you are going to be able to do that on the actual exam. So today, what we ended up doing was we made a lot of these, hopefully some connections, wrapping some things together. We looked at finding the position of a particle. A couple of things to pay really close attention to, not just with parametric motion, but really on the whole AP exam, is pay really close attention to what function is given. Go look at a bunch of AP problems. Go look on AP Central at FRQs. And here's what you're going to notice. Almost every single problem, they give you something, right? A graph, a table, or an equation, right? A graph of F, or a table of F, or an equation for F. And you look at the questions, they never seem to ask you about F. They never ask you about what you've been given. They ask you about something else. Here's a graph of F prime. Tell me about F. Or here's a graph of F. Tell me about G, right? They're always wanting to see if you can make those connections between things. So pay really close attention to what function you're given and what you're being asked for, so you don't fall into some of those easy traps. Be careful about finding position, which we did today, versus finding the distance traveled. Those are very different ideas. Think about the difference between speed and parametrics. That was just a number, right? Speed is a scalar. It's a number, but velocity is a vector, so it's going to be an equation. Typically in parametrics, it's going to be a different equation for x and for y. And then the slope of a tangent line, even though we're in parametrics, that doesn't change the meaning of a tangent line. When we talk about tangent lines to a curve, even if it's parametric, the slope of a tangent line is always going to be dy dx, and we looked about how to find that. So this is going to be your AP exam practice problem. And if you're still on, I want you to hang on a second, because I want to show you something at the end of this slide that's going to be really important, that I hope that you stick around for one more minute to check here before we jump onto your other AP sessions. But I wrote this problem late last night. I was inspired because there was a bug crawling across my actual computer screen, and I ended up disposing of it, and it left a mark on my screen. And I was like, I should pay tribute to this bug for giving its life for you. So in tribute to the bug, when I say bug, we're talking about like I thought it was an ant at first. It was very tiny. And so a bug is walking along a door, and I kind of drew this graph of this bug walking, and it ends up being knocked off of the wall eventually. So we got some nice little questions to wrap up what we talked about yesterday and Wednesday. And this last question is going to be really key, because on Monday, when we start with series and convergence and all that beautiful concepts that come with them, this is going to be a really good lead-in for that as Tony gets us jump started into that. So take a second and try this problem sometime before Monday. So what I wanted to share with you, and I hope you stayed on for this, is I want you to tweet out, okay? And I was probably supposed to get more permission, and I hope I don't get in trouble for this. If you don't see me for the rest of these, several weeks, then you're going to know that this was probably a no-no, but I think we're okay. This is my Twitter handle, PasswaterB, and then as well as my friend Tony's Twitter handle, it's AP Calc Teacher abbreviated. And we want you to tweet out and go ahead and tag us if you don't mind. But use the hashtags. If you're a student, hashtag AP Teachers Rock, and teachers, hashtag AP Students Rock. And what I want you to do, hopefully, is everybody right now is, we're a little bit stressed. We're trying to figure all this stuff out, and everybody's working super hard. I know that you guys as students are working really hard right now. Teachers are working so hard trying to make this work for everybody. So tweet out what you appreciate and love about your AP Calculus teacher or students. So if you're a student, tweet out what you love about your AP Calculus teacher or any AP teacher, really. And kind of tweet it out, tag me and tag Tony. And then each day, we're going to start out these sessions by reading some of those off. And we'll probably end up not identifying names and schools to protect some privacy and things like that. But we want to read off the things that you're saying. We want to read off what is good news right now, what's positive, and what should be highlighted instead of all of the unknown and kind of the uncertainties. So tweet us out. We want to see what you have to say. Tag me, tag Tony. Take a photo of this if you want to. That way you can get it. But we want to make sure that we share those, and we'll keep doing this all the way until May 1st. And I hope that we can start a trend of people sharing of all the great things that are happening with you guys and your teachers, and that way we can share them out. A very important announcement from the College Board that Tony shared yesterday, but we'll continue to share it. Look, we realize that not everybody has access to the internet, and this exam is going to end up being online, like we know. And so if you know any students or you are a student, please, please, please get this information to them. There's a simple website there at the bottom, cb.org/tech. And then they're going to find ways to make sure that you have what you need to take the AP exam. So that's going to be highly important. And then finally, thank you for watching. Tony said it best yesterday. We are incredibly amazed at the response of people who have been watching these videos. Look, Tony and I are just classroom teachers. We're regular guys, but we're so impressed with how many of you are doing so much to prepare. So every day for AP Calculus BC and all your other AP courses, find a way to get a little bit better, right? I always tell my students, get 1 point better today. If you get 1 point better every day, every session that Tony and I give, if you get 1 point better, that's 28 extra points. If you do that, you are going to be extremely successful on the exam. So thank you so much for watching. Don't forget to tweet out. I know already that there's a mistake in that warm up on part A. I think I have to finish it, and I will make sure that the key has the completed solutions for you. That way, if you did finish it and you caught that mistake, you can compare your answer to that. So don't forget, Tony will be here Monday next week at 9 a.m. And Tony will be giving a great lesson to introduce us to series, and we'll see you then. Have a great day.